So gamma rays are photons. They're just photons with very, very high energies. And their energies are so high that for all practical purposes, they behave like particles, which makes them exciting on one hand, but on the other hand kind of annoying to detect and handle, measure their properties. So you cannot treat them like ordinary optical photons. You cannot focus them. You cannot use mirrors to collect them. In order to measure their properties, make anything useful with them, you have to get them to interact with matter and produce something that you can measure, which is secondary particles, for example, an electron-positron pair and other products from that point on. So depending on their energy, we measure them in two ways. For energies low enough, and when I say low for gamma ray standards, I mean something like less than, say, 100 giga-electron volts. You want to do that in space. And the reason you want to do that in space is because they are absorbed in the Earth's atmosphere. So you fly a satellite detector that has heavy material in it, so that these gamma rays are encouraged to interact, pair produce, and then you measure that produced pair, which consists of an electron and a positron, and their path inside your detector. And from the energy they leave behind as they travel in the detector, and the direction in which this electron and positron are traveling, you can go back and infer what the direction and the energy of the original gamma ray was. Now, when you go to higher energies, that technique in principle can still work, but what happens is that you run out of gamma rays to measure. The higher the energy, the more rare these gamma rays are. So you are limited by the fact that you can only fly so much material into space. It becomes very difficult and it becomes very expensive. So what you would like to do is find a cheaper way to make a much bigger detector. So what you do is then you just stay where you are, sit on the Earth's surface, and use the Earth's atmosphere as your detector medium. This works best for higher energies because although the Earth absorbs the original gamma ray that's coming in, then what happens afterwards, which is the original creation of an electron-positron pair again, but these now are energetic enough to make more and more and more particles. We call that an extensive air shower. So that shower retains enough information so that if you track it by means of the light these particles emit as they travel in the atmosphere, you can again reconstruct the energy and the path of the original gamma ray. So that works best for energies above 100 giga-electron volts. We can push this technology down to maybe 10 giga-electron volts. So for that reason, we use Earth-based telescopes that are looking at the atmosphere, the light that is emitted from the secondary particles. We call this air Cherenkov telescopes.
So yeah, a neutrino is an elementary particle, as the electron is. So we know now actually some fundamental properties of the neutrinos, like the mass. So it's a very light particle, and in contrast to the electron, the neutrino is not taking part in the electromagnetic interactions. So it's also like the photon not taking part in electromagnetic interactions, and it only takes part in weak interaction. And so the weak interactions have the property that they are very weak, as the name suggests. So that means in order to detect these particles, so to do neutrino astronomy with these particles, you have to build very, very large detectors. So for example, there is a detector called IceCube at the South Pole, which consists of a cubic kilometer of ice. And so the way that we detect the neutrinos are via their charged and neutral current, weak interactions in the ice. For the case of very high energy neutrinos, you produce cascades. You can think of it as a very large shower of secondary particles created in this interaction, which then produces a visible signal in the detector in form of Cherenkov light. Or, for example, you can produce long-lived muons which are similar to electrons but are not stable. So these muons will travel through the detector and leave a trace of light behind. And so this would be a case of a track. And if we see these tracks, we actually have a very good angular resolution. So the track of the secondary muon will basically follow the initial direction of the neutrino. So if we measure the direction of this muon track in ice, then we also know the initial direction of the neutrino. And so in this case, we can do really neutrino astronomy with this. So yeah, we already talked about production of gamma rays by cosmic ray interaction with radiation and gas. The same is actually also true for the neutrino. So you can have charged and neutral pion production in cosmic ray interaction. The neutral pion will then produce high energy gamma rays, and a charged pion decay production and decay will produce a flux of high energy neutrinos. So this somehow goes hand in hand. So the sources which are producing gamma rays in this way will also be candidate sources for neutrinos. But for the neutrinos, we only have this one production mechanism. So for gamma rays, there are so-called leptonic processes which do not rely on the simultaneous production of cosmic rays. So if you see a neutrino, you have a so-called smoking gun signal for the acceleration of cosmic rays. And for that reason, it is a very valuable messenger in astronomy. There's also another advantage, that is, since the neutrino is so weakly interacting, it is not, first of all, not bent in any extragalactic magnetic field, and it is also not absorbed by other radiation backgrounds in the universe. So whereas photons or gamma rays at PeV energies have actually very strong absorption over cosmological distances, this is not true for neutrinos. So you can actually look very, very far back into the universe.
That's a very good question. Gamma rays can be produced by the interactions of ultra-high energy cosmic rays with either matter or light, photons. So the benefit that comes from gamma rays is that they do not bend in magnetic fields, they're neutral particles. So you can use them as a tracer of where charged particles, ultra-high energy cosmic rays were and where they interacted. And that information can then travel to you without any more bending in the magnetic field, and you can learn something about ultra-high energy cosmic ray sources. So there are two ways that you can get such photons, such gamma rays. One is very near the source. So you have some astrophysical source that produces ultra-high energy cosmic rays, the highest energy particles in the universe. And as these travel inside the source, then they interact with either matter or light within the source, and then they produce photons, gamma rays. In that way, you can see, by looking for these sources in the sky, where these protons might have been accelerated. Now, the problem is that this is not a decisive way to tell where very highly energetic protons of the high energy cosmic rays have been. And the reason is because other processes that do not involve protons can also create gamma rays. So although gamma rays are very essential in this indirect search for ultra-high energy cosmic ray sources, they are not what we would call a smoking gun. It's not like you'll see gamma rays and you know for sure protons are there. Fortunately, there is a particle that can tell us that, and this is the neutrino, which can only be produced when energetic protons or energetic nuclei have been there. But Markus will tell us more about it.
So some people say this is somehow the beginning of high energy neutrino astronomy. So this is the first high energy signal that we discovered in neutrino astrophysics. So there are many questions related to this newly found excess. First of all, the energies that we would see these neutrinos are related to cosmic rays which are in an energy region where we cannot be sure what kind of sources produce these cosmic rays. Usually you make the distinction between galactic cosmic rays and extragalactic cosmic rays. Galactic cosmic rays dominate at lower energies, extragalactic cosmic rays at higher energies, and the cosmic rays responsible for this neutrino excess sit somewhere in between, so we don't really know what kind of sources produce these neutrinos. So one thing that we have to understand now is what is the source population. If it is a galactic source population, there might be possibilities to look for association of these neutrino events with some galactic structure, maybe the galactic plane or the galactic center. If it is an extragalactic contribution, it will be mostly isotropic. So at the moment, we cannot really distinguish these two kind of signals because we have a very low statistics at the moment. And and there are also some interesting spectral features. So the energy dependence of the signal that we see suggests that there's a cutoff at high energies. And by studying the spectral features, we can also try to distinguish between different sources of high energy cosmic rays. So at the moment, this is a fairly new signal, so we do not have any definite answer, but this is certainly something that we will follow up in the future with more data in ICQ.
Thank you.